This is the last section on hypothesis testing, and this gets into something that's a little bit different from the previous ones in that up until now, everything we've done with hypothesis testing, we've assumed that we had the population standard deviation. The reality is oftentimes you will not have the population standard deviation. You'll have the standard deviation for a sample, but not for the entire population. So you remember a couple of the examples we've had to actually calculate the sample mean from a set of data, and we were mysteriously given the population standard deviation. Of course, that won't always happen. We may have to calculate it ourselves. So what we'll do is we'll actually go back to those t-charts from Chapter 8, and we'll use t-tests instead of z-tests. The procedures are pretty close. The one big difference is the way that the charts are handled. And so if you look at the formula is almost identical, right? For z-tests, we did the sample mean minus the population mean over population standard deviation divided by the square root of n. For t-tests, we're going to again use the sample mean minus the mean from the null hypothesis, except here it's going to be our sample standard deviation. Sometimes we'll be given the standard deviation. I mean, there may be an occasion where we have to calculate it ourselves, but for these problems, for the most part, we're going to be given the sample standard deviation. You know how many are in the sample. Now you can calculate a t-score. The difference is this. Once you find that t-score, then you also need to know the degrees of freedom. Remember, the degrees of freedom is one less than the number in your sample. So this is what that t-alpha chart looks like. So if you had a score of like 2.3 and 14 degrees of freedom, so if you had t equals 2.3 and 14 degrees of freedom, you'd come down here to 14 degrees of freedom, whereas 2.3 is somewhere between these two numbers here. So then what you'll do is you'll come up to the top and you'll look at that little number down the bottom there, that little number down the bottom there. So somewhere between 0.01 and 0.025, that's your p. So you're going to end up with a range of p-values, unless you use something like StatCrunch or a graphing calculator. But if you're getting these strictly off the table, then that p-value is going to give you a range. So if you knew, for example, that your significance level was 0.05, then you would know right away, I can reject the null hypothesis because my p-value is not going to be any higher than 0.025. There are times when this test will be inconclusive using a table of values like this, because you may end up with an alpha that's somewhere in the middle of that p-value range, in which case you're going to have to rely on technology or something to figure out what that is. So here, let's try another one. Suppose you had a t-value of 1.75 with 23 degrees of freedom. All right, so here's 23 degrees of freedom. Where's 1.75? Ooh, it is real close to that 0.05. So it's between 0.05 and 0.025. All right, but it's still less than, so it's still less than 5%, so you have enough evidence to reject the null. Okay, if you were to do it the other way, then, if it were up to, let's say, between 0.05 and 0.10, then you would not have enough evidence to reject the null. The other thing, too, is if you change that significance level. So let's say you wanted it at the 1% significance level, then there's not enough evidence in this one up here to reject because it starts at 0.025. All right, so that's the big difference when you're using these t-values. All right, so let's take a look at this problem over here. Estimate the p-value, make a conclusion. This one's a left-tailed test. 17 items in the sample. Negative 1.426 is our t-value. All right, so t equals negative 1.426. N equals 17. So let's go up here and pull up our t-chart. 1.426 and n equals 17. So n equals 17 means 16 degrees of freedom. Right, always one less than the sample. So 16 degrees of freedom, right over there. And the number that we were given, 1.426. Well, where is that? That's between this number here and that number there. So look at the two numbers up on the top. One of them is 0.05, one of them is 0.10. Again, just remember that these things go in the reverse order of what we think, because it's the numbers here area-wise that increase, the numbers on the top actually decrease. So my answer is somewhere between 5% and 10%. Look at those two numbers that are on the bottom, 0.05 and 0.10. It's got to be between 5% and 10%. So what does that mean? Well, nothing without knowing what the significance level is. So if the significance level is above 0.1, then you would reject the null. If it's less than 0.05, then do not reject. Now, if your significance level for some reason is like 0.07 or something like that, then that's undecided. You don't have enough information at that point to decide whether or not to reject the null hypothesis. All right, let's try a couple of these. We're going to try it with the table, and then I'm going to show you how to do it on the graphing calculator also. So estimate the p-value, state the significance level. The null hypothesis should be accepted or rejected, not rejected, or no conclusion made. So the first one is a right-tailed test, n equals 11, t equals 1.246. So right-tailed, so I want it to the right of 1.246. So I come over here. How many degrees of freedom? 10 degrees of freedom. And 1.246. 1.246 is really way out there, right? It's to the left of 1.372. If I switch this over here, 1.246 with 10 degrees of freedom is out here somewhere, right? 1.246 is well below, which means that that p-value must be bigger than 0.10. Okay, so that one ends pretty quickly, because if the p-value is greater than 0.10, then most of the time you're not going to accept that. You're not going to reject the null. So that p-value is greater than 0.10. Now, there is a way to get a more precise p-value on your graphing calculator. All right, so if you grab your graphing calculator, and you notice right above the VARs button is a distribution button. I got a TI-83 Plus, so it's probably about 10, 15 years old, but it still works fine, and so we're going with it. So you get this by doing second in VARs. That gives you the distribution menu. All right, so second in VARs, and then you're looking for option number 5 that says TCDF, a t-score cumulative density function. If you are doing a right-tailed test, then the syntax is t-score, degrees of freedom, and an upper limit. Usually for the upper limit, I just use 10, because 10 standard deviations above the mean would be an enormous number. So for this one, for a right-tailed test, you would do a t-score CDF of 1.246 with 10 degrees of freedom and an upper limit of 10. So let's try it. I got a 10, hit that comma that's under the sign key. And so I got a 1.246, comma 10, comma 10. It thinks for a second, and it gives me 0.121 if I round it. Right, which is consistent with what we found, right? We found a p-value of greater than 0.10. When we calculated on the calculator, it gave us a p-value of 0.121. Okay, makes sense. All right, left-tailed test. Number of items in the set of 30. A t-value of negative 1.572. Well, my t-values only have positive, so let's scroll over here and get a positive 1.572 for 29 degrees of freedom. Okay, so here's 29 degrees of freedom. 1.572 is between these two numbers, right? Between 1.3 and 1.7 is 1.572. What numbers are they? Well, they're between, again, 0.05 and 0.10. All right, so if the alpha value was less than 0.05 or greater, then I would reject. If it was greater than 0.10, then I would not reject. If it were in between, then it's inconclusive. How do I do this on the calculator? Well, this time, it's a left-tailed test. So for my left number of standard deviations, I'm going to put in negative 10. The t-score then is negative 1.572, and the degrees of freedom are 29, right? One less than the number of items in the set. All right, so second in vars, I have my TCDF. I'm going to negative 10, comma, negative 1.572, and 29 degrees of freedom. And calculator gives me 0.063. And I think the homework is going to ask you, rather than to do a range, to do one of these, where either you use StatCrunch or the graphing calculator. All right, look at the two-tailed test down the bottom. Two-tailed test with n equals 8 and a really big t-score. So how do I do this? Well, pick one or the other. Pick either the left or the right, and then just double it. All right, so here, if I throw this in my calculator, I'll get a TCDF of, let's say, 3.725 with 7 degrees of freedom and a very high upper level. All right, this gives me 0.002. But because it's two-tailed, I've got to double it. So my p-value is actually 0.004, which means basically I'm rejecting the null hypothesis, right? Because it's rare that I would have a alpha value that's less than 0.01. So most of the times that would be rejected. All right, let's try a couple of examples here. All right, so let's take a look at this limestone fertilizer problem. Researchers tested soil treated with fertilizer, measured percent of limestone to see if the fertilizer had increased the limestone above its usual 2.3%. 2.3% sounds like an important number. That seems like that's the mean. Okay, so the mean for the null is 2.3. They took 10 soil samples, so n is 10. The sample mean was 2.5. Sample standard deviation was 0.149. Does it provide enough evidence at the 1% significance level that the mean treated limestone exceeds what is normally found in the soil? So my alternative hypothesis is that the mean is above 2.3. All right, first step is let's calculate that T statistic. So that T statistic is going to be the sample mean minus the mean from the null hypothesis over the sample standard deviation divided by the square root of 10. All right, so that gives me 2.5 minus 2.3 divided by 0.149 over the square root of 10. All right, I get 4.246, so 4.24 as my t-value. So now what I'm doing is I'm trying to run a t-test with a t-value of 4.24, 9 degrees of freedom, and it's right-tailed. So I could go back to my table, right? 9 degrees of freedom and 4.24 is off the charts, right? It's way below 0.005. Okay. What if I want to throw this on a calculator or like a StatCrunch or something to get a more accurate p-value? So I would do, under my vars, a TCDF. This one is right-tailed, so I would start with 4.24, 9 degrees of freedom, and I would go up to 10 standard deviations above the mean. All right, so let's throw that in there. 4.24, 9, 10. Very small number. 0.00086. which is consistent with my table, right? Because this is my p-value. The table told me that p was less than 0.005, which it is. It's just a lot less than 0.005. So clearly, p is less than alpha, so there's enough evidence to reject the null hypothesis. The data provides enough evidence to conclude that the mean amount of limestone in that treated soil is above the 2.3. So maybe that fertilizer is doing something, right? That's what I'm concluding from that small sample of 10 that I picked from. All right, let's try one about driving distances. Okay, 2005, the average car in the U.S. was driven 12.4 thousand miles. Survey of 500 cars in 2013 shows the sample mean was 11.8. Sample standard deviation was 6, 5% significance level. Can I conclude that the mean distance driven differs, right? Key word, differs from that in 2005. Why is it a key word? Because that's what I'm going to use to set up my hypothesis. The null hypothesis is that the mean is 12.4. The alternative hypothesis is simply that the mean is not 12.4. Okay? What do I know? I know the sample mean is 11.8. I know that the number of cars driven was 500. I know that the significance level is 5%. And the sample standard deviation is 6. From this hypothesis, the alternative hypothesis, I also know that it's a two-tailed test. So whatever I get for P, I'm going to have to double it so that I can figure out how to compare it to that 5% significance level. All right, so the first thing is let's calculate our T statistic. So let's take 11.8 minus 12.4, divide it by 6 over the square root of 500. If I do that, I get 11.8 minus 12.4. Take that as negative 0.6. Divide it by 6 over the square root of 500. I get negative 2.24. So let's use my calculator and do that TCDF with a left-tailed, and then I'll just double it. Okay, so I'll go 10 standard deviations below the mean. I'll use negative 2.24 as my t-value and 499 degrees of freedom. Let's see what I get. I get 0.013. Because it's two-tailed now, I want to double it. All right, so my actual p-value is going to be 0.026. Right, how does 0.026 compare to my significance level of 0.05? It's less than. So since p is less than alpha, then I can reject the null. Right? There's enough evidence to conclude that it's different. Not to conclude that it's higher or lower, simply to conclude that it's different. Before we wrap up, how would this have looked on a table? Well, on a t-table with 499 degrees of freedom, after a while it just goes up by 100. So how about 500 degrees of freedom? Our value is 2.24. So 2.24 falls somewhere in here between 1.965 and 2.334. So somewhere between 0.025 and 0.01. So between 1% and 2.5%. Is that what we got? Yeah, because between 1% and 2.5% is that initial value that then we would double. So we could have, if we had to read it off a table, say it's between 0.01 and 0.025. And then when we double that, because it's two-tailed, we'd get between 0.02 and 0.05. And sure enough, our p-value is between 0.02 and 0.05. It's close to 0.03. But we get a much better answer by using the calculator to give us a value because that t-chart only has certain values on it. Otherwise, it would be enormous. So in this case, if you can grab those numbers off the graphing calculator, it'll be much more accurate. All right, that's the end of t-tests for cases where we don't know the population standard deviation.